The new section is entitled Secants and Tangent. Since we're still in the circles chapter, we're talking about circles. You have a circle. A secant is really a chord. Here's a chord, but it keeps going. It's a line that crosses a circle in two places. There's a secant line. Secant line. It's a circle, it's a line that crosses a circle in 2 points. A tangent line, on the other hand, just touches the circle in 1 point, not the initial point I put down. This is a tangent line. It touches the circle in 1 point. You have your circle, a line, touches it in 1 point. That point is called a tangent line. Tangent line. Another line that crosses a circle in 2 places, we call it a secant line. 1 place, tangent, 2 places, secant. Good luck in trying to draw a line, a straight line, that crosses a circle in more than 1 place. In more than 2 places. Can't be done. Okay. Now, we have a fact about tangent lines. If you go from this, draw a line from the center of a circle to the point of tangency, you have a right angle. If you have a line that just touches the circle in 1 place, then if you go from the center to that point, it's a right angle. If you are, well, okay. Let's hold on. So we will call this a tangent segment. And you must learn these definitions. It's a ray. It goes from, make believe that's the line, but only keep the part that starts at the point of tangency and goes in one direction. I could have called that, just the dotted part, the tangent segment, and erase that. That's the tangent segment, the dotted part. Doesn't matter which half you keep. It goes from the point of the tangency out. It can even stop. It can be a line segment. This is neither here nor there. But at the point of tangency, that's where it starts, or if you want to say end, it doesn't matter. Okay? It doesn't go both sides of the line, both sides of point P. If it did, not a big deal. You can call that one tangent segment, and you can call that another tangent segment. But you wouldn't call the whole thing a tangent segment. Why? Definition. It starts from the point of tangency and goes out. Now, we need to be very, well, okay, this is not a tangent segment, because if I did continue, it's not tangent to the circle. It doesn't touch at one point. You may say, oh, come on. Of course that line touches the circle at one point. I agree with that. But first of all, it's not a line. If you extended it in both directions, then it's a line. That crosses the circle. Actually touched it in two places. If you have a line that just touches the circle in one place, and you only keep half the line. That's a that's a tangent segment. Okay? It has to be tangent to. If you extended it in both directions, it would really be tangent. And another definition. If you have this secant line and the whole thing is a secant line, if you have this secant line segment, we have a special name for this portion. It is called the external part. This is called the external part. Part of what? Of the secant line. Some books call this the secant segment. It's the whole thing. Okay. Now, we have this theorem, and this is the main theorem of this section. Now remember, circles are very, very symmetrical. You can't get any more symmetrical than a circle. Here's the center. If I take a point P out here, and I draw a tangent line through that point, and a tangent line through there. Okay? And I ignore this portion. I ignore that portion. I mean, I guess what I can do is just label this A and B. The theorem says that if AP, the theorem says if AP and BP are tangent to circle O, then those two lengths are equal. Then AP is actually congruent to BP. And why wouldn't it be? Basically, you just cut the circle in half, and the top half and the bottom half are mirror images. They just mirror images. And you may say, wow, you drew the line horizontally. Well, I mean, that's neither here nor there. If I draw the point P here, so here's B and here's A. Oops, there's A. But if I rotate this, okay, it's hard to see where P is, but P is right there. If I rotate it clockwise, well, then it will look just like my picture to the left. You know, you have a line of symmetry here. So yeah, they're going to be the same. But Just because we can see something doesn't mean we don't have to prove it. The nice thing about seeing it is you then know how to prove it. Sometimes. At least you know that it is valid. Okay. So now, how would we go about proving that AP and BP are the same length? Well, what I would do is I would draw OB, and OA. Well, those are equal. We have a very clear rule. A radii and a tangent line to a circle, they meet at right angles. AP is tangent to the circle. Oh, so when you draw a radii, it meets at a right angle. Now, and OB is also a radii. It meets PB at a right angle because BP is a tangent line to the circle. So these two are equal. Now I really am going to cut this in half. Clearly that equals itself. But if you look in the lower triangle and the upper triangle, they're both right angles. The hypotenuses are the same. And we have a leg that's the same. So by the High Leg Theorem, these two triangles are congruent. Okay, these two triangles are congruent. And the side adjacent to the right angle, excuse me, I just want to say it, okay, yeah. By the sides adjacent to the right triangle, but there's two sides adjacent. One with one slash and one with no slashes. We're talking about the one with no slash, the one that's now in blue. Adjacent to the right angle, we have one side with one slash and one side with no slashes. Since these two triangles are congruent, we can now say that AP is congruent to BP because these two sides are congruent parts of congruent triangles. They are in the same location. They are in the same location. You want to say it's opposite the side with X, but it's not the one with one slash? That's this side. You want to say it's the side opposite the X, but not the one with one slash? Well, then it's this side. Those are corresponding. It's very symmetrical. Of course they're going to be the same length. But we proved it. We proved the major theorem in this. Now, I guess I want to talk about two other definitions. This circle and that circle are tangent. They meet at one point. In fact, there's a tangent line. They met at one point. This circle and this little circle, they meet at one point. This point, there's a tangent line. These are both tangent circles. The top two are tangent circles, and the bottom two are tangent circles. These are external. These two circles are external tangent circles. You might see it more clearly down here when I call these internal. One is inside the other. One circle is inside. Internal tangent circles. These two circles are outside one another. They are called external tangent circles. They just meet at one point. These two circles are not tangent circles. This circle and that circle, they're not tangent circles. They're not meeting at one point. They meet at one point, they're tangent circles. There's two ways that can happen. One circle is inside the other, or they're both, or no circle is inside the other. Okay, so let us do a handful of problems and we will be done. Suppose you have this nice round circle. You have this point tangent, and you go here to point P. A, B, P. And you are told that AP is 15 centimeters. And you're also told that the radius is 8 centimeters. The radius of circle B is 8 centimeters. And you want to find BP. BP. How long is BP? Okay. See, and this is a very, very simple problem. You need not to panic. AP is 15. Draw that radius, which is a right angle. And the radius is 8. So now you're done. You can find BP. Use the Pythagorean Theorem. You want to call this x for right now? Call it x. 8 squared plus x squared is equal to 15 squared. So x squared is 15 squared minus 8 squared. You can add those two numbers, get 23. Subtract the two numbers, get 7. Multiply those two results. 7 times 20 is 140. 7 times 3 is 21. It's 161. Remember, a squared minus b squared. You can add those two. And whatever that result is, multiply it by a minus b. And that's all I did. I mean, you could say 15 squared is 225. 8 squared is 64. And you get 161. I think, well, that's 161, sorry. So that is what x squared equals. So x squared is equal to 161, and x is the square root of 161. And x they called BP. So BP is the square root of 161. To the best of my knowledge, I don't know the square root of a number that goes evenly into 161. If I'm wrong, I'm sorry, but I doubt it. Should always try to break down your square roots. Okay, let us consider this problem. Let us consider this problem. You have a point P outside, and it's tangent to the circle here, and it's tangent to the circle there. There being, say, Q and R. And the center is at O. Okay. So you're given that PR and QP are tangent to the circle. That's given. And you want to prove the following. You want to prove that PO bisects angle P. It bisects angle P. Angle RPQ. This angle right here. You want to prove that PO bisects it. Okay. Well, we kind of just did this problem. You remember I drew this and that, and I showed that triangle 1 and triangle 2 were congruent? Well, this angle and that angle are corresponding parts, and as a result, they're going to be congruent. Okay, so we have a right angle here and a right angle here. And OR and OQ are equal to one another. And clearly OP equals OP. So you have this upper triangle, number 1, and the lower triangle, number 2. They are both right angles. The hypotenuse are equal, opposite the right angle. And again, when I say equal, I mean congruent. And they have another leg that are congruent. By the High Leg Theorem, they're congruent. Triangle 1, triangle 2 are congruent. And, okay, and you know, we even prove that those two are the same. But basically, corresponding parts of congruent triangles show that RP and QP are congruent. It's, okay, it's the side opposite the side with the X, but not the one with one slash. It's that one. Both of those are opposite. What's opposite the side with X? Which side? That side and that side. Or what you can argue is, it's the side that doesn't have one slash or an X. This side. The side that doesn't have one slash or an X. It's that one. Those are corresponding. Now, this angle P is on one end of the side that has one slash. It's not the one with the right angle. This angle over here is at one end of the side that has one slash, but not the one with the right angle. Oh, you mean those corresponding ones? They're equal. It bisected it. Basically, you could have put this problem as part B of the last one. Once you had corresponding triangles, triangle 1 and triangle 2, the top half and the bottom half are congruent, you can then say that those two angles by P are congruent to one another, and hence are congruent. Here's a nice problem. I like this one. We even put these on axes. X-axis, Y-axis. You have one circle, and you have another circle. They are tangent to one another. They are tangent to one another. You have P, you have Q, you have the center of the bigger circle at R, and S. So P is the center of one circle, R is the center of the other circle, and Q is right here. That didn't seem to come out well. And you were told some facts. P is at 0. R is at 19,0. And you want to find Q and you want to find S. And let's find QR. How long is QR? Well, remember, that point right there is 0, 0. That is, right here X is 0 and right here X is 8. that means the radius of the smaller circle is 8. So where is Q? Go another 8. Q is at 16, 0. Okay. Now, they told us that R is 19 over. You go 19 from one end point of a circle to the center. That's 19. Well, if you go the other way, you're going to go another 19. S is at 38, 0. S is at 38, 0. And what's QR? Well, Q is 16 on the x-axis. I mean, everything's on the x-axis. And R is at 19. From 16 to 19 is 3. That finishes that problem. So we can even put in x and y axes. It's a nice problem. You have two circles. They do not intersect. But in the last, they each have centers. But this is a tangent line to both circles. This is a tangent line to both circles. P, Q, R, S, and if needs be, T. I want to prove a few things. I want to prove that angle P is equal to angle S. That is, the angles by the centers are the same. I also want to prove that PT divided by, it's going to be ST is equal to, let's see how we're going to, which one we're going to do. QT over TR. Okay, so now first thing I will say is tangent, QR is tangent to both circles. Okay, that means we have right angles here and here. And opposite angles are equal. We have two triangles. The top left one, the bottom right one. By the no choice theorem. By the no choice theorem. And if you have two triangles and they have two congruent angles, two pairs of congruent angles, well then the third pair must be congruent. Angle P equals angle S. Now, we actually have that these two triangles are, I don't know if I want to say congruent yet, they are similar. The right one is clearly smaller than the left one. So when two triangles are similar, because all we have is angle, angle, angle. We just have the three angles corresponding. Remember what we talked about. If you have a triangle like this, and you put it under a magnifying glass, it becomes like this. That angle is that angle, this angle is this angle is this angle. The magnification isn't going to change that. And you can't say, well, come on. I mean, we all know that this angle is bigger than that one. And this angle is bigger than that one. And this one, this angle down here, is bigger than this little bitty one. Nonsense. There's 3 angles, and both of those triangles still add up to 180. If they're all bigger than that little one, the corresponding little ones, it'd have to add up to more than 180. Okay. So the congruent sides give the same ratio. In other words, if these are 2 congruent triangles, and this side are congruent, they correspond. You know, they both have angle 1 here, and angle 2 here, and angle 3 here. Okay, angle 1s are equal, angle 2s are equal, or congruent if you prefer. This is between 1 and 2. This is between 1 and 2. If this is 4 and this is 3, well, the sides are in the ratio of 4 to 3, which means if this is 12, then this is 9, because it has to be the same ratio. 12 over 9 reduces to 4/3. They're proportional. So you divide their 2 corresponding sides. One from the large divided by one from the small. And you take another pair, one corresponding. One from the large, one from the small. These 2 ratios should be the same. Now, PT is this one. It's the hypotenuse. It's the one opposite the right angle, divided by the one opposite the right angle, TS, or ST. This is going to be the same as, now, we've used up PT. I can talk about PQ, QT. They're suggesting we talk about QT. QT, where is this? QT is right here. It's between the right angle. One end point of the line is a right angle, and the other end point is 1 slash. 1 slash right angle. That's the side that has 1 slash and 1 right angle. RT, TR. And you say, oh yeah, they are true. I can say one other pair. I can talk about PQ. PQ is between 2 slashes and the right angle. RS is between the right angle and 2 slashes. I could have said this statement. I could say PT over ST is PQ over RS. I could say that QT over TR is equal to PQ over RS. These are the 3 that I could have been asked to prove. They only asked me to prove one of them, which I did. So it's pretty neat that when you have that picture, we have their corresponding, we have similar triangles. All right. Now, suppose you have a circle and its center is 3, 5. And over here you have a tangent line, and this point is 5, 7. This point right here is 5, 7. What is the slope of the tangent line? Well, I'd find the slope of this line. And remember, it meets at a right angle. Let's find the slope of the blue line. Remember, it's a change in y with a change in x. Y goes from 5 to 7. It went up 2. Oh. Well, okay. X goes from 3 to 5. It went up 2. The slope is 1 over 1. Now, the slope of the perpendicular line, you switch this. The top goes to the bottom goes to the top, and you change the sign. If this slope would have been 2/3 the slope of the perpendicular, you flip it over and you change the sign. But it wasn't that. You flip this over, you get 1 over 1, and since this number is positive, you say negative. The slope of this line is -1. It's a negative reciprocal. Okay. Suppose you have one line that's tangent to 2 circles. Amazing, huh? You have one line that's tangent to 2 circles. This one line is tangent to this little circle. Oops, there's the line. And it is also tangent to that bigger circle. Call the centers Q and R. In fact, if you connected the centers, they meet with the tangent line at, say, point P. And we'll call this point S and this point of tangency T. They want us to conclude that, say, PQ divided by PR is SQ divided by TR. Whenever I see ratios, I think similar triangles. Well, remember that the point of tangency to the center of a circle, they meet at right angles. This is a right angle. Okay, and in the little triangle, Q, S, P, you have a right angle and you have angle P. In the bigger triangle, you have P, R, the right angle T. It also has angle P. Oh, so by the note, so these are not congruent triangles. Of course not. One's inside the other. They can't be the same size. By the no choice theorem, the third angles have to be the same. And that's enough for me. PQ is in the little triangle and it's opposite the right angle. And the big triangle opposite the right angle is PR. PQ is the PR as, now they say SQ. SQ is between a right angle and an angle with 2 slashes. Right angle, 2 slashes, TR. And that's what it says over there. So here it's true. Those 2 triangles are similar. So they have the same 3 angles. And when you divide corresponding parts, you always get the same ratio. Okay, let's try one more problem. Just be daring and try one more problem. you have an isosceles triangle, A, B, C, and you put a circle inside it. Nice, perfectly round circle. And you call the points where it meets P, Q, and R. P, where it meets the circle. Sorry, the triangle. P, Q, and R. And it's obvious, you know, AB is congruent to AC. Those are the two congruent sides, and you have the inscribed circle, PQR, centered at, well, let's not use C, centered at O. And you want to prove that BR and RC are the same. BR and probably RC. BQ, yeah, of course, and CQ. You want to show that each of these are the same. Well, if you think of that, you have this really, really nice symmetrical triangle. It's symmetrical down the middle. What is the chances that you can put a circle here that's also going to touch this line? If you put a circle that touches this point and say it touches that point, well, it's going to touch the mirror image. It's going to touch this one. Case of year, it's going to be that this and this are the same. It's logically sound. And AB and AC are tangent to the circle. AB, so this is given. You're given that AB and AC is tangent to circle O at P and Q, respectively. And you want to prove that those bases are the same. That QC is bisected, or Q is the midpoint of BC. All right. So what we would do is, I would just draw that, whether it ends up helping us or not. Now, I know that this is a right angle, and I know that this is a right angle. And I also know that this angle and that angle are equal because BA and CA are congruent. These are equal to one another. Give those two slashes. Now, it looks like I have 4 triangles. Let's talk about above QA. I have 2 triangles. I have BQA, the big one, and then I have POA, the smaller one. Okay, for whatever it's worth, that's the same because it's the radii. It's the same as the other two. I think this one's going to be a little bit tricky. Let us ignore this side for a moment. I claim that those three angles in the middle are the same. I claim that these three angles, they are, oops, not there, but there, that those three angles are the same. Let us draw this picture a little bit bigger. Let us start off with a bigger circle. Tangent, tangent. A, B, C. AB is tangent at P and Q. Right. Now, here is the center. I know that this length and this length and that length are the same. But no, that does not mean they cut off the same arcs. And I know this angle and this angle are the same. And this is 90 degrees, and this is 90 degrees. Okay. And this is point Q. If I do this, all right, so we're going to use some theorems that we've already done, that we know. If I ignore all of this for the next minute or so, if I ignore all of that, basically you have a circle. I can even ignore this here. We've already proven that this angle and that angle are equal. And if two of the three angles are equal, if you have two pair of congruent angles in two triangles, well then the third pair are equal. Those are equal. So we know that. And now we extend it. We extend the fun. And we also know that those are equal. Okay. Now, we even know from an earlier theorem that PA and QA are equal. But we know that AB and AC are equal. That means the balance are equal. Those are equal. What do you add to PA and QA? The same amount to get BA and CA, or AB and CB. All right. And I could extend this without any loss. Okay, let me put 2 slashes. Now, if you look at the big top triangle and the big bottom triangle, they both have those 2 equal, and they both have those equal. Oh, but that's enough for me. Those 2 angles are equal. Those 2 angles are equal. But they lie in a straight angle. Angle Q is 180. So both of them are 90 degrees. They are both 90-degree angles. They are both 90-degree angles. So, by the High Leg Theorem, remember, we were told that AC and AB were the same lengths. Okay, so actually, let us just draw their bigger triangle. Sorry, the 2 bigger triangles down here. I'm going to have to scale them down a bit. But we have the big triangle here, QBA, 1 slash, 2 slashes, and a right angle. And right underneath it, I'll draw it very separately. We have QAC, right angle, 2 slashes, 1. And of course, QA is equal to one another. Well, by angle, side, angle, angle, side, angle, these 2 triangles are congruent. These 2 triangles are congruent. And this side is between an angle with 2 slashes and a right angle. And this side is made, on one end it has a right angle, and the other end it has 2 slashes. Therefore they're corresponding. Therefore they are equal in length. Okay, that completes this section on secants and tangents. Know the one theorem. Just know the one theorem. And use it whenever need be. Whenever you're having trouble, think about the theorem of the section.